Welcome to Evo AI, where we navigate the intriguing evolution of artificial intelligence. I'm your host, Bogdan Yanku, and in this series, we'll explore how artificial intelligence is transforming the way we work, innovate, and grow. From small startups to corporate giants, we'll unravel the mysteries of AI, uncovering insights, strategies, and the real-world impact on our everyday lives. Whether you're in sales, finance, marketing, human resources, or just curious about artificial intelligence, Evo AI has something for you. Welcome to AI Unlocked. In today's episode, we're changing direction a little bit and we'll be diving deep into the realm of machine learning, a powerful form of technology that's reshaping industries around the globe. But what is it about machine learning that's capturing the attention of businesses, researchers, and innovators? Well, let's explore. But before we do that, just allow me to quickly remind you that you can get our show on Spotify, Apple, Google Play, iHeartRadio, Amazon Music, and Radio Public. Now let's get back to our show. Machine learning powers many of the technologies we interact with daily, from the chatbots that assist us online to the predictive text on our smartphones, and even the shows Netflix suggests for our next binge watch session. It's the force behind the language translation apps, the content in our social media feeds, and the autonomous vehicles that promise to revolutionize transportation. But what's exactly machine learning? At its core, machine learning is a discipline that enables computers to learn from data without being explicitly programmed. This shift in approach is not just academic, it's actually practical. A 2020 Deloitte survey revealed that a staggering 67% of companies are harnessing the power of machine learning, with 97% planning to integrate it in the coming year. From manufacturing to retail, banking to bakeries, businesses across sectors are leveraging machine learning to unlock new value and enhance efficiencies. As MIT computer science professor Alexander Marty aptly puts it, machine learning is changing or will change every industry. Leaders, therefore, need to grasp its basic principles, potential, and limitations. However, it's not just about the technology. The societal, ethical, and social implications of machine learning are profound. Dr. Joan LaRoviere, a pediatric cardiac intensive care physician and co-founder of the nonprofit The Virtue Foundation, emphasizes the importance of using these tools for the greater good. She believes that machine learning holds immense potential to better the world, and it's our collective responsibility to ensure it's harnessed ethically. So, as we embark on this journey to understand machine learning's role in industry and beyond, it's essential to remember that it's not just about algorithms and data. It's about the transformative potential of technology, the challenges it presents, and the promise it holds for a better future. Artificial intelligence, as defined by John McCarthy, the father of AI, is the science and engineering of making intelligent machines, especially intelligent computer programs. AI is a computer program that performs something smart. It can be a complex statistical model or an if-then statement. The if-then statements are simple rules programmed by humans. Considered together, all the if-then statements are sometimes called rules engines, expert systems, knowledge graphs, or symbolic AI. Such AI is normally referred as to weak AI, bound to perform only a certain range of tasks. In contrast, strong AI understands itself well enough to self-improve with capabilities akin to human intelligence. Machine learning is a subset of AI. This means all machine learning is considered as artificial intelligence, but not all AI counts as machine learning. Machine learning has the ability to scale itself when exposed to more data, unlike expert systems or knowledge graphs. One of the most important aspects of machine learning is that it doesn't require any human intervention to make changes when required. This makes it highly efficient. In essence, machine learning can be described as the process of developing a computer system on how to make highly accurate and reliable predictions when provided with data. These predictions could be accurately recognizing speech or spotting humans or traffic signs in front of a self-driving car. Let's talk briefly about the three types of machine learning. Number one, supervised learning. Task-driven learning where the machine is trained using labeled data. For instance, images of cats and dogs are labeled and fed into the machine for training, and the machine must identify them. Number two, unsupervised learning. Data-driven learning where the model identifies patterns and relationships in the dataset by creating clusters. It doesn't rely on labeled data. And number three, reinforced learning. The machine learns to react to an environment. They interact with the environment and find out what could be the best outcome. The machine learns from past experience and tries to capture the best possible knowledge to make accurate decisions based on the feedback received. Deep learning is a subset of machine learning. In a broader sense, it is a technique for realizing machine learning. Deep learning algorithms are inspired by the information processing patterns observed in the human brain. To accomplish this, deep learning uses a layered structure of algorithms called an artificial neural network, or ANN. The design of an ANN is inspired by the biological neural network of the human brain. This makes machine intelligence more proficient than standard machine learning models. Let's compare machine learning with deep learning. Deep learning is a subset of machine learning and takes data as an input. After being fed with data, it makes intuitive and intelligent decisions using the artificial neural network. Machine learning, on the other hand, takes data as an input, computes it, and tries to make decisions based on the training it got. Deep learning is used to extract insightful features from the raw data. It doesn't depend on features like local binary patterns or histogram of gradients. Machine learning depends on such features. Deep learning performs well with more data, while machine learning algorithms perform well even if the dataset is small. Deep learning requires more computational power, often needing GPUs or TPUs, while traditional machine learning algorithms can be performed using a CPU. Deep learning network training time could be extensive, ranging from a few hours to months. Traditional machine learning algorithms can be trained within a few minutes to hours. The problem-solving approach in machine learning is more segmented, while deep learning models can learn to localize and classify on their own. Machine learning algorithms are usually simpler to decode and are widely used in businesses, while deep learning algorithms, even if they can exceed humans in terms of performance, are still not as reliable when it comes to deploying them in business. In conclusion, while AI provides the broad network of mimicking human intelligence, machine learning offers the tools and techniques to make this a reality, and deep learning further refines this with neural networks and large datasets. Let's explore now some of the core methods and machine learning techniques that everyone should be familiar with. Ensemble methods combine several predictive models to achieve higher quality predictions than each individual model could provide on its own. Think of it as building a bicycle by selecting the best parts from various locations. Once assembled, the resulting bike outperforms any single source option. In the machine learning world, the random forest algorithm is an ensemble method that combines many decision trees trained with different datasets. As a result, the quality of its predictions is higher than that of a single decision tree. Essentially, ensemble methods help reduce the variance and bias of a single machine learning model. Many top winners of Kaggle competitions use ensemble methods, with popular algorithms including random forest, XGBoost, and LightGBM. Neural networks aim to capture non-linear patterns in data by adding layers of parameters to the model. Deep learning is built using artificial neural networks, which involves networks with many hidden layers. Deep learning techniques require vast amounts of data and significant computational power, making them especially effective in areas like image classification, text, audio, and video processing. Popular software packages for deep learning include TensorFlow and PyTorch. Imagine training a model to classify images as shirts, t-shirts, and polos. Now you need a similar model to classify images of pants as jeans, chinos, casual, and dress pants. Can you transfer the knowledge from the first model to the second? Yes, with transfer learning. This method involves reusing parts of a previously trained neural net and adapting it to a new, similar task. The main advantage is that you need less data to train the neural network, saving both time and computational resources. Reinforcement learning is a machine learning method that helps an agent learn from experience. By recording actions and using a trial and error approach in a set environment, RL can maximize a cumulative reward. For instance, reinforced learning was used by AlphaGo, an RL-based algorithm, to beat the best Go player in 2016. While reinforcement learning is powerful, especially in gaming scenarios, it can take a very long time to train for complex problems. Natural language processing is a technique used to prepare text for machine learning. It's not a machine learning method per se, but is essential for tasks involving human language. NLP can help with tasks like auto-completing text messages or correcting misspelled words. The most popular package for processing text is NLTK, or Natural Language Toolkit. Word embeddings capture the context of a word in a document, allowing for arithmetic with words. Word2Vec, for instance, maps words in a corpus to a numerical vector. These vectors can then be used to find synonyms, perform arithmetic operations with words, or represent text documents. For many data science tasks, we typically have a training dataset with known labels. However, the amount of label training data is often limited. One solution to this is creating additional training data using the pseudo-labeling technique. This involves using the model to make predictions on unlabeled data. The most confident model predictions are then used as additional training data labels. The model is then retrained on both the original training data and the new pseudo-labeled additional training data. This new model might produce a better score than the original one. The rationale behind this is that additionally collected data might incorporate slightly different relationships and signals than the model can learn from. In summary, machine learning is a vast field with a plethora of techniques, each tailored to specific tasks and challenges. From basic methods like regression to advanced techniques like deep learning, the landscape is ever evolving. Machine learning, at its core, is deeply rooted in mathematical concepts. While it's tempting to bypass the math and just jump straight into using pre-built libraries and tools, a profound understanding of the underlying mathematics is crucial for anyone aspiring to master the field. This understanding not only aids in algorithm development, but also in interpreting results, diagnosing issues, and innovating on existing methods. Linear algebra is foundational to machine learning. It provides the structure and operations needed to systematically represent and manipulate data. For instance, datasets are often represented as matrices, with rows corresponding to individual data points and columns to features. Operations like matrix multiplication can correspond to data transformations or even the computations within a neural network. Why is linear algebra so pivotal? It offers a systematic basis for the representation of simultaneous linear equations. For example, consider two linear equations. Solving for their variables can be straightforward. However, in datasets with potentially thousands of observations and variables, manual computation becomes infeasible. Linear algebra, with its matrix operations, provides the tool to handle such large-scale problems efficiently. Multivariate calculus, particularly the concept of partial differentiation, plays a crucial role in optimizing machine learning algorithms. Take gradient descent as an example. It's an optimization algorithm used to minimize the cost function in models like linear regression. The idea is to compute the gradient, or the direction of steepest ascent, and then move in the opposite direction to minimize the function. This involves calculating partial derivatives of the cost function with respect to the model's parameters. The process is iteratively repeated until the algorithm converges to the minimum value of the cost function. Probability is the mathematical framework that quantifies uncertainty. In machine learning, it's used in various forms, from the basic Bernoulli and Gaussian distribution to more complex structures like Bayesian networks. Concepts like probability density functions, cumulative density functions, and Bayes' theorem are fundamental. Bayes' theorem, for example, provides a way to update probability estimates based on new evidence. It's the foundation of Bayesian machine learning models, which offer a probabilistic perspective on learning and have been applied successfully in numerous applications. Statistics is the discipline that allows us to make inferences from data. In the context of machine learning, statistical concepts help us understand data distributions, testing hypotheses, and validating model results. Key concepts include measures of central tendency, like mean, median, and mode, measures of spread, like variance and standard deviation, and hypothesis testing tools, like p-values. While advanced machine learning models, such as deep neural networks, might seem far removed from basic statistics, foundational statistical concepts still play an important role. For instance, understanding the distribution of input data can be crucial for pre-processing steps, and hypothesis tests can be used to compare the performance of different models. Concluding, the mathematics behind machine learning is obviously vast and multifaceted. While it's possible to use machine learning algorithms without a deep understanding of the underlying math, true mastery in the field requires a solid grasp of these mathematical foundations. Whether it's the linear transformations of linear algebra, the optimization routines from calculus, the uncertainty quantification from probability, or the inferential tools from statistics, each play a pivotal role in making machine learning the powerful tool that it is today. Machine learning, as a subset of artificial intelligence, has a rich history filled with groundbreaking discoveries, achievements, and milestones. Let's take a journey through time to understand the evolution of this transformative field. 1763. Thomas Bayes' work, An Essay Towards Solving a Problem in the Doctrine of Chances, is published, laying the foundation for Bayes' theorem. In 1943, Warren McCulloch and Walter Pitts developed the first mathematical model of an artificial neuron, making the birth of neural network research. 1950, Alan Turing proposes a learning machine that could learn and become artificially intelligent, foreshadowing genetic algorithms. 1952, Arthur Samuel begins work on some of the first machine learning programs, creating programs that play checkers. 1957, Frank Rosenblatt invents the perceptron, generating significant excitement in this field. 1967, the nearest neighbor algorithm is introduced, making the beginning of basic pattern recognition. 1970s, the AI winter occurs, characterized by pessimism about machine learning's effectiveness. 1980s, the rediscovery of backpropagation causes a resurgence in machine learning research. 1990s, machine learning shifts from knowledge-driven approach to data-driven approach. Support vector machines, or SVMs, and recurrent neural networks, RNNs, gain popularity. 2000s, unsupervised machine learning methods such as support vector clustering become widespread. 2010s, deep learning becomes feasible, leading to significant advances in vision and text processing. ImageNet, a large visual database, becomes a catalyst for the AI boom of the 21st century. 2012, the AlexNet algorithm achieves a breakthrough in image recognition, popularizing deep neural networks. 2014, Facebook's Deep Face system achieves a 97.35% accuracy in face recognition, rivaling human performance. 2016, Google AlphaGo program becomes the first to beat an unhandicapped professional human Go player, showcasing the power of combining machine learning with tree search techniques. 2017, the transformer architecture is introduced by Google's Brain, allowing for faster parallel training of neural networks on sequential data. 2021, AlphaFold 2 achieves unprecedented accuracy in protein structure prediction, scoring above 90 in the global distance test for around 2/3 of the proteins. The history of machine learning is a testament of human ingenuity and perseverance. From the foundational work of Bayes in the 18th century to the recent advancements in deep learning and protein structure prediction, the field has witnessed remarkable growth and evolution. As we continue to push the boundaries of what's possible, one can only imagine what the future holds for machine learning and its transformative potential. The industrial sector has been a pioneer in adopting transformative technologies to enhance operational efficiency, innovate processes, and reduce costs. Machine learning, with its capability to process vast amounts of data and derive intelligent insights, is playing a pivotal role in revolutionizing numerous industrial applications. Let's now explore the more recent advancements and techniques in machine learning tailored for the industrial domain. Machine learning techniques can be broadly characterized into supervised and unsupervised learning. Effectively, supervised learning utilizes labeled datasets, where each data point is paired with a meaningful label. It excels in tasks like data classification and regression, such as predicting energy consumption based on various parameters. And unsupervised learning operates on unlabeled datasets, discovering hidden patterns without external guidance. It's frequently employed for clustering, which is grouping of similar data, and association, finding relationships among data. Key machine learning models for industrial applications. Number one, linear regression algorithms. Linear regression, a supervised learning technique, is employed to estimate a variable's value based on other continuous variables. For example, in an industrial setting, it can predict energy consumption considering factors like equipment size and operational hours. Number two, clustering model, k-means plus algorithm. An enhancement of the k-means clustering algorithm, k-means plus partitions observations into distinct clusters. Each observation is associated with the cluster having the closest mean. This technique is invaluable in industrial scenarios like inventory characterization, where items can be classified based on shared attributes. Number three, neural network algorithm. Drawing inspiration from human neural structures, neural networks process data using sensors, measurements, or direct input. Comprising node layers, including input, hidden, and output layers, neural networks in industries can optimize energy consumption, oversee equipment health, and forecast maintenance requirements. And number four, decision tree algorithm. Primarily used for classification problems, decision trees function with both continuous and categorical variables. They produce easily interpretable rules and highlight fields crucial for prediction and classification. In industries, decision trees facilitate quality assurance, process enhancement, and predictive maintenance. Let's look at some industrial applications of machine learning techniques. Energy optimization. Leveraging algorithms like neural networks, industries can achieve optimal energy consumption. By analyzing variables such as ambient temperature, prevailing utility rates, and equipment usage patterns, machine learning models can offer real-time monitoring, alerts, and maintenance suggestions. Quality control. Decision trees can ascertain if a product adheres to specifications. By juxtaposing various attributes against specification benchmarks, industries can guarantee product quality and minimize defects. Industry management. Clustering algorithms, especially k-means plus, assist in classifying inventory items based on shared characteristics, promoting efficient storage, retrieval, and stock replenishment. Machine learning is heralding a new age of productivity and innovation in the industry realm. From fine-tuning energy consumption to assuring product quality, the latest machine learning techniques equip industries with the arsenal to address intricate challenges and elevate operational standards. Let's cover now some industrial applications of machine learning. Predictive maintenance is one of the core applications of machine learning in manufacturing. By analyzing patterns in data collected over time, machine learning algorithms can reasonably predict when a machine may need maintenance. This approach is crucial as unscheduled maintenance can deeply cut into a business bottom line. Predictive maintenance ensures that machinery has as much uptime with the fewest delays as possible. Expensive IoT sensors that record vital information about the operating conditions and status of a machine make this possible. These sensors can capture data points like humidity, temperature, and many more. The supply chain roles from a manufacturing center are also being improved with machine learning technologies. Production is only one element. Machine learning technologies such as logistics route optimization and warehouse inventory control make up a cognitive supply chain that continues to evolve in the manufacturing industry. For instance, AI-powered logistics solutions use object detection models instead of barcode detection, replacing manual scanning. Computer vision systems can detect shortages and overstock, allowing managers to optimize inventory shortage. Using neural networks, high optical resolution cameras, and powerful GPUs, real-time video processing combined with machine learning and computer vision can complete visual inspection tasks better than humans. This technology ensures that products are of the highest quality and that unusable products are eliminated from the system. In the past, machine learning's use in video analysis has been criticized for the quality of video used. However, with high-quality cameras and greater graphical processing power, neural networks can more efficiently search for defects in real time, without human intervention. Energy consumption forecasting is vital for optimizing every part of the factory. The most common way to do this is to use sequential data measurements, which can be analyzed by data scientists with machine learning algorithms powered by autoregressive models and deep neural networks. These models can define trends, cyclicity, irregularity, and seasonality of power consumption, allowing factories to optimize their energy use. Thanks to the IoT sensors powering predictive maintenance, machine learning can analyze the patterns in the data to see what parts of the machine needs to be maintained to prevent failure. If certain patterns lead to trends of defects, it's possible that hardware or software behavior can be identified as causes of those defects. From there, engineers can come up with solutions to correct the system to avoid these defects in the future. Generative design is where machine learning is used to optimize the design of a product. With data and a desired goal, machine learning can cycle through all possible arrangements to find the best design. Machine learning algorithms can be trained to optimize a design for weight, shape, durability, cost, strength, and even aesthetic parameters. This approach is crucial for creating environment-adaptive robots that can operate efficiently in complex industrial settings. Let's cover now some case studies as to why industries choose machine learning for industrial applications. One of the leading manufacturers of heavy machinery employed machine learning to predict when their equipment would fail. By analyzing sensor data from machinery, machine learning models could identify subtle patterns that indicated an impending failure. This allowed the company to perform maintenance only when necessary, reducing downtime and saving costs. Techniques like regression analysis and time series forecasting were pivotal in this transformation. Another example is of a major power company integrated machine learning to optimize its smart grid operations. The machine learning models process data from various sources, including weather forecasts, demand predictions, and real-time grid status to optimize energy distribution and reduce wastage. Clustering and regression algorithms played a significant role in achieving this efficiency. One other example in another field, a global logistics company employed machine learning to enhance its demand forecasting accuracy. By analyzing historical shipment data, market trends, and external factors like economic indicators, the machine learning models could predict demand with higher accuracy, leading to optimized inventory levels and reduced holding costs. Techniques such as ARIMA and PROFIT were used for these predictions. Another example from another industry. A chemical production company used machine learning to monitor and ensure the production process. Machine learning models could detect anomalies and deviations from the desired quality standards, prompting immediate corrective actions. Classification algorithms like SVM and decision trees were instrumental in this quality assurance process. Now, moving into mining, in this industry, determining the grade of ore is crucial for operational efficiency. A leading mining company employed machine learning to predict ore grades based on geological data and past drilling results. This allowed the company to optimize its extraction processes, ensuring that high-grade ores were processed first. Regression techniques and random forests were key in these applications. Moving to agriculture, agricultural enterprises are leveraging machine learning to predict crop yields. By analyzing data from satellite images, weather forecasts, and soil sensors, machine learning models can forecast the yield for specific crops. This assists farmers in making informed decisions about irrigation, fertilization, and harvesting times. Neural networks and regression models are commonly used for these predictions. Moving to another industry, In textile manufacturing, ensuring fabric quality is absolutely paramount. Machine learning models trained on images of both defective and non-defective fabrics can automatically detect defects in real time as fabrics move through production lines. Convolutional neural networks, or CNNs, are the backbone of such defect detection systems. In oil and gas companies use machine learning to simulate reservoir performance. By analyzing seismic data and drilling logs, machine learning models can predict how reservoirs will behave over time, allowing companies to optimize extraction strategies. Techniques like Gaussian processes and k-means clustering are employed in these simulations. Moving into the construction industry. A construction conglomerate integrated machine learning into its operations to monitor safety compliance in real time. Cameras placed around construction sites feed data to machine learning models which identify safety violations such as workers not wearing helmets or harnesses. This proactive monitoring has led to a significant reduction in on-site accidents. Steel industry, a major steel producer, employed machine learning to optimize its steel production process. By analyzing data from various stages of production, the machine learning models could recommend adjustments to parameters like temperature and pressure, ensuring optimal steel quality and reducing wastage. Regression analysis and neural networks were central to this optimization. These case studies that we presented before highlight the transformative potential of machine learning in the industrial sector, emphasizing its role in optimizing processes, ensuring quality, and enhancing operational efficiency. Let's move on now and cover some of the challenges in industrial machine learning. In an industrial setting, data comes from a plethora of sources. This includes machinery condition monitoring systems, process control and monitoring, administrative systems, and various documentation sources. Integrating this data to form a cohesive dataset for machine learning applications can be a significant challenge. The vast and long-term storage of data should ideally be a perfect base for machine learning. However, hurdles such as associating data channels with relevant meta information, ensuring data integrity, and dealing with missing documentation can make data integration a very complex task. Industrial processes are inherently specialized. This means that there is no one-size-fits-all solution when it comes to machine learning models. A solution developed for one industry or even one plant might not be directly applicable to other. This specialization affects the scalability of machine learning solutions, making it challenging to develop models that can be universally applied across different industrial sectors. Industrial applications often require real-time data processing, whether it's for monitoring machinery in real time to prevent failures or for optimizing processes on the fly. The need for instant decision-making is paramount. This demands machine learning models that not only process data in real time, but also make accurate predictions and decisions without delay. In industrial settings, safety is of utmost importance. Machine learning models, while powerful, must be reliable enough to ensure that their predictions or decisions do not compromise the safety of the operations. This is especially crucial in sectors where even a minor error can lead to significant safety concerns. For many machine learning applications, especially supervised learning, data annotation is crucial. This involves connecting the observed data to the ground truth to make it interpretable. In the industrial context, this annotation can only be performed by domain experts familiar with the specific processes or assets. Given the complexity of industrial processes and data, this becomes a significant bottleneck. Industrial processes are specialized by nature. It's challenging to directly apply a solution developed for one sector to another. Even within the same plant, different processes might require distinct approaches. This lack of universal solutions means that every machine learning projects in the industrial domain require a degree of customization, making them more complex and potentially more expensive. While industries might have vast and long-term data storage, making this data useful for machine learning applications presents challenges. Issues like associating data channels with relevant meta information, ensuring data integrity, and dealing with missing or out-of-range values can hinder the path to data readiness in industrial applications. Data annotation in industrial domain often requires the expertise of professionals familiar with specific processes or assets. This dependency on a select group of experts can slow down the machine implementation process and can be a significant challenge, especially when compared to other domains where data annotation is more straightforward. By understanding and addressing these challenges, industries can harness the full potential of machine learning to optimize their operations, improve efficiency, and drive innovation. Some challenges in industrial machine learning, especially when we're talking about cybersecurity and data corruption. Data poisoning is a significant threat to machine learning models. In this type of attack, adversaries tamper with the training data of a machine learning model, impacting its ability to produce accurate predictions. The goal is to introduce malicious data points that, over time, skew the model's behavior in a way that benefits the attacker. For instance, in a cybersecurity context, if an industrial system uses machine learning to detect network anomalies indicating suspicious activity, an attacker aware of this model can introduce data points that decrease the model's accuracy. Over time, this could mean that malicious activities go undetected. A real-world example of data poisoning is seen in attacks against email spam filters. Attackers try to skew the filters by reporting large amounts of legitimate emails as spam, thereby confusing the model and reducing its effectiveness. Machine learning models, especially in industrial settings, are becoming prime targets of cyber attacks. As industries increasingly rely on machine learning outputs for decision making, security experts warn of adversarial attacks designed to exploit these models. For instance, attackers might try to influence recommendation systems on platforms by using fake accounts to manipulate upvotes, downvotes, or shares. Moreover, attackers can exploit the information leaked about how a model works. Therefore, it's crucial to maintain strong access controls for both the model and the training data. Over-permissive data access or weak security protocols can lead to data poisoning attacks. The difference between an attack that evades a model's prediction and a poisoning attack lies in its persistence. With poisoning, the attacker's goal is to have their malicious input accepted as training data. This type of attack is more prolonged and might take weeks or even longer depending on the model's training cycle. Correcting a poisoned model is challenging. Since poisoning typically occurs over multiple training cycles, pinpointing when the model's accuracy began to shift can be difficult. Reverting the effects would require a historical analysis of inputs to identify and remove the malicious data. In cases with vast amounts of data and numerous attacks, retraining might not be feasible. Given the challenges of rectifying poisoned models, the focus should be on prevention and early detection. Measures like input validity checking, rate limiting, regression testing, manual moderation, and using statistical techniques to detect anomalies can be effective. For instance, a small group of accounts or IP addresses shouldn't dominate the model training data. Comparing newly trained classifiers to previous ones can also help in early detection. As industries increasingly adopt machine learning, the importance of understanding and mitigating cybersecurity threats cannot be overstated. Data poisoning and other cyber attacks targeting machine learning models pose significant challenges, emphasizing the need for robust security measures, continuous monitoring, and proactive defense strategies. As we've journeyed through the intricacies of machine learning, its distinction from broader AI concepts, and its profound impact on the industrial domain, a few key takeaways emerge. Unlike traditional AI systems that operate based on predefined rules, machine learning thrives on data. This data-driven approach ensures that decisions are not just automated, but are refined and optimized based on real-world feedback. In industries where precision can translate into significant cost savings or even safety implications, this attribute of machine learning is invaluable. One of the hallmarks of machine learning is its ability to adapt. As new data streams in, machine learning models can adjust, ensuring that they remain relevant and effective. In dynamic industrial environments where conditions can change rapidly, having systems that can evolve is crucial. Industries often grapple with vast and complex data sets. Machine learning's strength lies in sifting through this data, identifying patterns, and making sense of what might seem as random or chaotic to the human eye. This capability is especially vital in areas like predictive maintenance, quality control, and supply chain optimization. As industries grow and data volumes expand, the need for scalable solutions become paramount. Machine learning, with its ability to handle large-scale data efficiently, stands out as a future-ready solution. While machine learning offers numerous advantages, it's essential to acknowledge and address the challenges it presents, from data integration to cybersecurity threats. By being proactive and informed, industries can harness the power of machine learning while mitigating potential risks. In closing, as industries continue to evolve in this era of rapid technological advancement, it becomes evident that the future isn't just about creating intelligent machines. It's about fostering machines that can learn from their experiences, adapt to changing scenarios, and grow in their capabilities. That's the transformative power of machine learning. This is where we stop today, our venture into the amazing world of machine learning. Thank you for listening to AI Unlocked. If you enjoyed this episode, please leave us a review and share it with your friends. For more episodes and additional information, please visit our website at evoai.ai and subscribe to our newsletter. See you in the next episode. Well, that's a wrap of today's episode of Evo AI. We've delved into the fascinating world of artificial intelligence, unlocking insights that are changing the face of business today and tomorrow. But the exploration doesn't end here. There's always more to discover. Well, I'm Bogdan Janku, and this has been Evo AI. Together, we're part of something bigger, much bigger, a movement towards understanding, innovation, and growth. Well, if you enjoyed our journey today, don't forget to subscribe, and please join us again as we continue to explore the future of AI in business. Until next time, keep evolving.